Testing. 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 What's going on? Why can't I see it here? Testing, testing. Testing. All right, I think we're good. Cool. Welcome to another Hoopo stream. Happy Friday. If you guys are excited for the weekend. Today we got, we're going to be looking at the Vesuvius Challenge. So this is a challenge that has been announced, and I think it's in partnership with Kaggle, as far as I understand, but basically, I don't know, rather than trying to describe it, let's just actually go ahead and read the introduction that they have. So it starts off with a story, and I thought that, you know what might be funny is if we actually just get one of our voice clones to read it for us. So let's copy paste this text here. Let's put it into 11 Labs. And who do you guys want to read this? You guys would rather have Donald Trump, Joe Biden, Elon Musk? Let's do Donald Trump because he's the most outrageous one. Let's put this in here. All right, let's see. Let's get his intro.
20 meters of hot mud and ash bury an enormous villa once owned by the father-in-law of Julius Caesar. Inside there is a vast library of papyrus scrolls. The scrolls are carbonized by the heat of the volcanic debris, but they are also preserved. For centuries, as virtually every ancient text exposed to the air decays and disappears, the library of the Villa of the Papyri waits underground intact.
Okay, so you guys heard it there. So basically, there's Pompeii was this big volcanic eruption that happened in the Roman era, and basically it buried this giant Roman city. I don't know if it was a city, maybe more of a village, but it buried this Roman village, and it kind of like preserved a bunch of the artifacts there. And one of the things that it preserved was these huge collections of scrolls. So you have 600 unopened scrolls. But the problem is that they're burnt to a crisp, right? They're basically these like big blobs of like basically carbon, right? And up until now, they've tried to kind of like peel them apart with tweezers, and it just doesn't work, and they're just basically breaking the scrolls, and it's not leading anywhere. So what they did is they basically took these scrolls and they put them in a particle accelerator, right? So the particle accelerator has a very, very fine kind of measurement resolution in 3D space, and they were able to get basically information from that, right? So 4 to 8 micrometer resolution with this particle accelerator, and then that means that they basically have 16 bits of density data per voxel, right? So if you guys remember, voxel is a unit of measurement of 3D space. So you have a 3D volume, and then within that you have voxels. So basically now they have a 3D scan of these lumps of charcoal that used to be papyrus. And what they figured out is that, hey, maybe we can actually read what's on these papyrus by analyzing this 3D data with some kind of machine learning algorithm, right? Because burnt papyrus, I don't know what it's made out of. I guess like the reed, it's made out of like grass, right? The paper in Roman times, was it made out of lambskin, or was it made out of paper, wood pulp? One of those things. But wood pulp with ink and wood pulp without ink produces two different types of, it's going to look different with that X-ray. So basically you have this giant garbled mess of 3D space that they've scanned of a papyrus, and it's, okay, can we actually read the words off of this? So they've opened this up, and they've created this challenge, and the grand prize for 700,000 US dollars, which might be worth 1 Bitcoin, if Balaji is right, but if you can read at least 4 separate passages of continuous and plausible text and at least 140 characters long. In each passage, at most 15% of the characters can be missing or illegible. Qualifying submissions reviewed by a team of developers. So, realistically, the grand prize probably not going to be a random individual developer such as myself. This is going to be a team. This is going to be people who have tens of thousands of dollars to spend on compute. These are going to be people with A100s. So this isn't really what we're going for. We're mostly just doing this for fun, but what we're targeting, realistically, like a goal that we could potentially reach, is this ink detection prize. So if you can get some kind of ink, you get 50 grand. So that's basically the challenge. You can see here the different sponsors for this challenge, and it's a little bit of famous people here. You have Toby Luke, the Spotify guy. You have John and Patrick Collinson. These are the founders of Stripe. Daniel Gross, this is another kind of person within the VC and startup community in the Bay Area. So you have a couple kind of technocrats here sponsoring this, and I think it's just a bunch of good fun. And to me, the interesting part too is that I think that all the nerf stuff that we've been doing this week is exactly the right kind of mindset for this. I feel like too many people are going to be trying to do like 2D approaches, like ConvNets, even things like vision transformers, and I don't think that's actually the right solution. I think you're going to need to do something 3D, and then you're going to have strong geometric priors, and then it's going to come down to like sweeping over hyperparameters of these strong geometric priors of like some kind of scroll or something like that. That would be my guess, but obviously I haven't really looked at this, but let's go deeper. Okay, so they have the prizes, the data, 3D X-ray scans of 2 unopened scrolls, and scans and images of 3 papyrus fragments. The current best tools and techniques for virtually unwrapping the scrolls. Let's go ahead and open that in a new tab. And a community. Discord server to ask questions, receive updates every 1 to 2 weeks, and follow at Scroll Prize on Twitter. So let's go ahead and follow that. Let's follow these guys. So you can get a rough idea of how many other people are currently competing on this right now. 359. So not the worst. You know, we've seen a lot of Kaggle challenges where you have thousands of people. So this one seems a little bit under the radar. Here are the scrolls. So these are the 2 scrolls that they scanned. You can see how mangled they are. They just look like an overcooked hot dog or something. This is a little 3D visualization of the actual 3D scan of the scroll. Machine assistant tools through any means necessary. Why is this difficult? As you will read, advanced tools and techniques exist for virtual unwrapping. This was demonstrated in 2015 when they unwrapped a specific scroll. Okay, so we're going to have to read these tutorials. Finding the ink. The ink used in the Herculaneum, I think this is the village, or the town that was at the base of the mountain of Pompeii, or the volcano, is radiolucent, making it difficult to see in the scans. Train a machine learning model which can detect the ink from subtle patterns in the 3D X-rays. Models are not yet perfect and probably need to be improved. Applying the ink detection models to the segmented scrolls has not yet been fully demonstrated. Okay. We believe that it is possible to read the scrolls. Yeah, so you see here you have a little voxel and it's going through, and here they're basically showing you that It's kind of like a binary classification problem. For every voxel of 3D space, you want to be able to predict whether or not it contains ink or it does not contain ink, and then you need some kind of mapping function of this voxel in 3D space corresponds to this particular position in the 2D space of a scroll. So there's two different problems here. There's the classification problem of ink, no ink, which is going to be in 3D space. And then there's the mapping problem of going from the 3D scroll that's all tangled up into a 2D flat plane, which you can then read. We have some ideas that future progress. Okay, so basically, the only thing that's really available right now is up until June 14th, 2023. Basically, they have this ink detection prize on Kaggle. Okay, cool. Next thing here, the data. Oh my God, 4.7 terabytes of data. That is insane. Okay. 8 micrometer 3D scans of 2 intact scrolls, scanned in horizontal slices from bottom to top. Each scroll is 14,000 TIF files, 120 megabytes each. So let's understand that a little bit. What is a .tif file with respect to an X-ray machine? A TIF file is a tagged image file format for storing high-quality lossless images. All right, so no compression. In the context of an X-ray machine, a TIF file may be used to store digital images produced during an X-ray. So it might be kind of like an MRI that does like slices. It can store resolution without a loss of quality. Crucial when examining medical images. Supports multiple layers. Can use for aspects, annotations, or image enhancements. Okay, so it's the multiple layers. It's kind of like maybe like a PDF, but for images, if I had to guess. Okay. Each slice, each scroll is about 11.2 centimeters tall, so something like this. Both were scanned at 54 electron volts. And then we also have a smaller slice. Yeah, there's different power levels that you can use for the X-ray, and they're going to result in different data for sure. Four micrometer 3D X-ray scans for 3 broken off fragments of papyrus. I think this is the test data set, basically. So this is the actual, or actually it's the opposite. This is the test data set is actually significantly larger than the trained data set, which is kind of weird, right? Usually you have a very large training data set, and then you have a small test data set that you have to perform well on. Here it's the opposite. You have a very small training data set, right? Because they only have these 3 little fragments with the ground truth, ink or no ink. And then the test data set is actually this giant 4 terabyte data set here. So Kaggle data post-process version of the fragments data. 2 operations were done. The 3D were transformed into surface volumes as described in this tutorial. Okay. And infrared photos were aligned with these surface volumes, and binary ink masks were created to denote the presence of ink. So binary classification. And I guess campfire scroll, maybe this is like they took a little scroll that also had the same kind of ink, the same kind of paper. The archaeologist told them exactly what kind of paper and ink they would be using, and then I guess they burnt it. So they have kind of another training data set here with a fake scroll that they made. Fill out the registration form and you will be provided with a download link automatically. The tutorial data is available to download without registering. Let's download that. Vesuvius Challenge. Let's download it. Hopefully it's not terabytes. I don't have the bandwidth to download a terabyte of data here. Click that. Open link in new tab. Do we have it? Is it here? ls downloads. ls-lht downloads. No, we still don't have it. Why is this not working? Let's get this scroll data. Let's get it. Okay. Maybe we can download it off Kaggle. You want some more coffee? All right. If you are just entering the Kaggle competition, you do not need to download any data from this page. Okay, that's good. All the relevant fragment data is available via Kaggle. Good to know. Where did the data come from? Are from the Institut de France, scanned using a diamond light source particle accelerator. There's a paper associated with this. What does this data look like? Okay, so this is actually individual scans, so holy shit, you can see how mangled this looks, right? This is a scroll, right, which is basically a cylinder that like spirals like that, and you can see how complicated it is, right? It's not, you basically have these pieces and they wrap all the way around. It's like, that's going to be very messy, but it's not impossible. So fragments are sliced, so they're kind of sliced horizontally like that. Okay. Let's go into the tutorials here. Okay. Technical overview. I like these little GIFs that they made. These are nice little GIFs. Share the current best tools for virtually unwrapping and reading. Our expectations you will build on these techniques. Scanning, creating a 3D scan of a scroll. Segmentation, using layers of rolled papyrus. And ink detection. Each of these steps has been shown to work. That is your goal. Before we dive, and their radiolucent ink. Okay, this is like how they did it. They took a piece, they blasted it with some x-rays, and then they used tomographic reconstruction techniques. Okay, this is them kind of going up and down through the scroll, so you can see the images here of 560 by 560, which is good, you know. 560 by 560 is something that we can fit on a GPU here. If it would have been like significantly larger image sizes, it would have probably been a little bit too hard. Another thing I'm noticing here, this is not color, right? This is a single channel image, so it's going to be 560 by 560 by 1. 16-bit precision on the individual number. Each pixel represents a cube. Okay. That's the actual 3D volume. Capture the 3D shape of the layers. Each individual surface is called a segment. Okay, you see here they're basically going from volume to mesh. Oh shit. We use an in-house tool called a volume cartographer to manually annotate a surface on one of the slices, and then the software extrapolates it along the z-axis to other slices. Okay, so this is the kind of mapping problem that I was talking about, right? And this, oh my god, dude, this seems outrageous. But basically someone traced out an individual line from one of the kind of wraps around the papyrus. Yeah, I just don't feel like that's ever going to be applicable. You're not going to be able to do that for the inside. It is not sufficient to only examine the voxels. We do not want to sample voxels around the mesh. We only need the voxels which are close to our segment. Okay, so they're basically doing a little bit of topology here. They have the surface of the papyrus on the outside, and then they can basically put a little air bound on the top and bottom and then unflatten that out. The output is a flattened 3D volume that has been sampled around this mesh, which we call a surface volume. It is much smaller than the original volume and consistent since the papyrus is flat. Okay, ground truth data alignment. This is the actual training data set that they're going to have on Kaggle probably. Surface volume containing sheets. Manual step is to label where we believe there is ink using a line infrared photo. Ooh, not all dark areas are ink. Some are shadows, burn marks, and other types of damage. So that's going to be a little complicated. I wonder if they have more than that, right? If it's just ink, no ink classification, there might be less signal than if you know shadows, burn marks. So ideally you'd have almost like a 4-way classification. You'd have no ink, or you'd have empty space, papyrus with no ink, papyrus with burn marks or any other type of damage, and then papyrus with ink. So it's 4-way classification per voxel. That's what I'm thinking. Okay, and then, yeah, once you do this for pretty much every single surface that you can extract, then eventually you can translate this. Right, and I think once you have actual like letters and ink, then getting it to a point where you can read it is fine. Cool. Let's actually look at the Kaggle. So now we're on Kaggle. Why don't we actually try to sign in? I think I have like a Kaggle account. Yeah, there we go. Let's join this competition. Sure. I accept. Okay. Let's look at the data. Ooh, 32 gigs of data? Damn. Come on. That's way too much. Okay, so the files, you have a train and a test. You have fragment ID. You have surface volume, image ID. Let's actually start downloading this so we can... summary. I want the data explorer. Can I just download this data? How do I download this data? This is just the sample submission. Can I download the train dataset? Download all. All right, here we go. 20 gigabytes. It's going to take 7 minutes. Okay, so while that's downloading, let's actually read a little bit more. So each X-ray surface contains a grayscale slice in the Z direction. So Z is up and down the scroll. Each fragment contains 65 slices. Combined, this gives us a width times height times 65 number of voxels per fragment. You can expect 2 fragments in the hidden test set, which together are roughly the same size. Mask.png, so this is the actual prediction. This is the ground truth. A binary mask of the ink versus no ink labels. Okay, so actually you have 2 different masks here. You have a mask which is telling you empty space versus papyrus, and then a mask which is telling you papyrus with ink versus papyrus. Run length encoded version of the label. So run length encoding is a way to store metadata that's a little bit more efficient. Coco also does this. There's a couple different object detection and specifically with things like masks. Like segmentation masks can get very, very expensive to store in something like a JSON file or a CSV file. So basically there's this way of storing it called run length encoding, where it's a little bit lower memory, but I don't know, it's also not great. Infrared photo on which the binary mask is based. Example submission file. Okay. This is the same format you should make your submission in. All right, so I think the first thing we need to do here is we should go on GitHub and let's make a new repo for this. Let's go ahead, repo, new, and we're gonna call this Vesuvius. Actually, let's come up with something cooler here. Let's say, who was the patron deity of Pompeii? The patron deity of Pompeii was Venus. What is can you give me the name of a GitHub repo for a Kaggle competition based on Venus and Pompeii? Okay, blah, 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 come on. Okay, it's not. I just want the name of a GitHub repo, which I will create. Just give me a name that sounds cool based on Venus, Pompeii, and ancient Rome. A cool, relevant name for a GitHub repository based on Venus, Pompeii, and ancient Rome could be Venusian Pompeii Legacy. Give me 10 other cool names. Stop generating. Give me 10. Here are 10 additional cool names for a GitHub repository based on Venus, Pompeii. Eternal Venus Pompeii, Pompeii Love Chronicles, Venus Pompeii Empyrean, Ashen Venus, Celestial Pompeii Rune. I like this Ashen Venus. All right, let's do that. Ashen Venus. Okay. Entry to the scroll or the Vesuvius challenge. We're going to make this a public. We're going to add a README. Of course, our license, we're going to choose MIT because we're not corporate slaves. And git ignore, let's just choose a standard Python git ignore here. Python. Let's create this repository. All right, so we got our Ash and Venus. Let's go ahead, let's copy this link here, and then we can open up a terminal. Let's actually not open up this one. Let's go into our thing here. Let's go into our dev folder. Let's clone our brand new little Ash and Venus repo in here. What? Is one of you guys hacking me? What the fuck is this? Someone could be eavesdropping you? What are they eavesdropping on? I don't create any interesting code. Alright, who cares? If you're hacking me, you don't know what the fuck you're doing, because I don't actually have anything worth hacking. It didn't even clone it. Oh my god, we gotta remove this key. Jesus. Okay. We have our Ash and Venus. Now let's go ahead and see if there's a nice code that we can start from. Example submission, ink detection tutorial, TF data pipeline, TensorFlow. I'm not going to want to use TensorFlow. Fuck that. I'm going to definitely use PyTorch. It seems like this one is the most popular. So 94 upvotes here. Currently gold. Right, so there's a leaderboard. This guy here, Igor Kresheny. All right. Let's go to code here. Keras, unit. No, we just want this one. Okay, what was he using here? You have some buffer size, learning rate. Subvolume data set. Generating pixels. Classifying. Okay, this is really what I want. I want this like RLE function, run length encoding. Okay. So let's go into our thing here. Let's open up a VS Code. I'm going to put that there. Let's create a file here. We're going to call it utils.py. Inside utils, I'm going to copy paste this RLE function here. Right? I don't want to rewrite this crap, this run length encoding. Let me minimize this, make this a little smaller, just because I can't see what's going on. Okay, there's a couple. We need import numpy as np. What else do we need here? I think that's the only thing we need. There's also this threshold parameter. We're going to have to add that as a kwarg. What is the value of the threshold parameter? 0.4. Okay. And first thing I'm noticing right now is we don't even have a Conda environment for this. So let's go ahead and make a Conda environment. So let's go here. Let's say Conda create. We're going to call this Ashen Venus. Okay. Conda activate Ashen Venus. Then we are going to pip install NumPy. Okay. Let's make sure to use, we're going to have to switch this to Ashen Venus. All right, perfect. Let's also format this. Let's go back. Okay. So we could probably make a Jupyter notebook here. That might be actually the best way to do that. You know what? Why don't we use PyTorch 2.0? Let's set up a little requirements file here. So touch requirements.txt. Okay. Let's pip install the same version of PyTorch that we were using yesterday for Nerf Studio, because ultimately I'm kind of eventually going to go there. Torch Vision, FuncTorch, or whatever. We don't actually need to be like super anal about that, so let's go here, clear, pip install torch vision, collecting torch 2.0, CUDA 1110, okay, cuDNN, torch vision, let's also put in here pip freeze -- local. It's not exactly what we want. I think let's just do pip freeze -- local, and then we'll grep torch in that. So these are the versions of the torch that we have. Actually, wait up, this isn't even the torch GPU. Import torch. Torch.cuda.isAvailable. True. Okay, we're good. So copy that. Put that here. Let's get rid of that torch audio. Let's do pip freeze local. We're going to grep NumPy. This is the version of NumPy that we have. And we're going to put that there. Okay. Let's go into our README. Ashen Venus entry to the Vesuvius Challenge. Let's put a link to this right here, the scroll prize. Copy link address. We'll do this. Let's do installation, or actually we'll call it setup. conda create. Actually, wait up. You can dump a conda environment. Dump conda environment into a YAML file. Instructions for dumping conda environment into a YAML file. Conda env export. Okay, that's what we want. So let's do conda env export into environment.yaml. And let's do, let's see what's in that. Jesus Christ, yeah, this is like so much crap in it though. I don't want half of this crap. Conda create, Ashen, Venus. You could also use this. Or and then pip install requirements file, or you could just install it like this. All right, so let's go ahead and commit these. Let's just say environment setup. We're going to add all that, and then we're going to commit. Okay, now let's create a new file. We're going to save this. We're going to call it EDA for exploratory data analysis.ipynb. All right, so now we have our little Jupyter notebook. Let's go ahead and bring this over here. Go back to the example that they're doing here, and let's start copying some of this crap in here. So what happens if we copy paste this entire thing here? We're probably not going to have specific dependencies. Install. It's installing the Jupyter Notebook dependencies. No module named matplotlib. All right, so we need matplotlib. Pip install matplotlib. Does not get into account all the packages that are installed. Is the source of the following dependency. Seaborn requires SciPy, which is not installed. Okay. Pip install SciPy. Okay. Let's re-export into the environment.yaml. And let's restart the kernel. And let's rerun it. IPyWidgets. Pip install IPyWidgets. Okay. Back to here. Restart the kernel. Rerun it. No file or directory. Kaggle input Vesuvius challenge train 1 ir.png. Okay, so we don't actually have the data. So let's go ahead and into our terminal, we're going to copy the from the downloads. Okay, here it is, the Vesuvius challenge in detection.zip. Let's unzip that. And Vesuvian, and let's unzip it here. Okay. So it's inflating it. We're going to have to change this path here. This is going to be just dash train. And here in our git ignore, we don't want to like commit these things, so let's go here and we'll say data folder. Data, but also train. Test. And output. Okay. So this makes sure that Git won't commit the stuff that's in these folders. All right, well, that's going. We can copy paste this stuff here. Copy paste this. More code. Copy paste this. Okay, here's the actual model that they're doing. It's a 3D convolution. And then this is the actual data loader here. I wonder what they're doing with these buffers. It seems a little complicated. Split our data set into train and val. Training. Okay. Is this done yet? Damn, no, it's still unzipping. That's fucking crazy. .3D conv followed by a 3D max pooling, another 3D conv followed by another 3D max pool, another 3D conv and another 3D max pool. Then one big flat, then a multi-layer perceptron here with a 128, followed by a ReLU, followed by a single neuron, right, because this is a binary classification problem, and then a sigmoid to turn that into a nice probability. And then two device here, right, where the device is going to be CUDA if torch is CUDA available, else CPU. Okay. Plus code. Generating pixel lists. This is the actual training loop here. Let's see what they're doing. Pixels inside and outside the rectangle. There's still this like buffer crap. I don't know what that is. You're creating the train data set, train data loader with a batch size. Binary cross entropy loss. Standard, your generic gradient descent here. And then they have learning rate scheduling. Okay, fancy, fancy. And then here's the actual code. There's no logging here, I'm noticing. All right, so that's the train. This is the eval. Is this the same RLE function? PD data frame from dict. This we're going to need for sure. So let's go into our utils. We have our RLE function. We're also going to need a make submission function. Let's close that. For fragment and enumerate test fragments. Fragment.name. ID predicted. This right here. Import pandas as PD. And I don't really like the default dict object. I also don't know what list is. Is list just the type list, or is this like a name of something? So you have your test fragments, you have your predicted images. Okay, we're probably gonna have to modify that. We got sample submission, ID predicted. Okay, this is the run length encoding here. Let's put a new folder. We're going to call this data, and then we're going to have a new folder, and we're going to call this output. And we're going to put the test and the train into the data folder. Move. And then we're going to put the sample submission into the output folder so we don't commit those. Okay. So we have too many things open. Let's close all of them. Let's reopen this. Let's go back up here. Let's run this cell. No such file dash train. This should be dash data. Rerun it. No such file dash data dash train 1 ir.png. Data dash train dash 1. This should be just data. All right, there we go. So all of our dependencies are working. So let's go ahead and freeze our stuff. So conda save. I already forgot the conda command. History grep conda. What was the command to export? Conda env export. And then pip freeze dash dash local into requirements.txt. Okay, so now we have all of our dependencies. Let's go ahead and save all of that. So we have our git ignore, we have our exploratory data analysis. We have our environment. Actually, let's clear the outputs here. Clear all outputs and save. Because you don't want to save outputs. You have your environment YAML. You have our requirements. And you have our utils. Okay. Dependencies working. Commit to sync changes. Okay. Go. This is opening the ink labels, turning it into a float, putting it on the device, which in our case should be the GPU, creating some axes, setting the title, puts the label to the CPU, I am sure, okay. Mass.png, ink labels.png. Okay, if we actually switch to here, cd data train, and then we'll do 1. And let's do Nautilus dot. Okay, so inside this first scroll fragment, which is, there's 3 of them in this training data set, we have the R run length encoding CSV for the ink, we have the mask, we have the ink mask and the IR, and then whatever this surface volume is. This is just a bunch of, this is the actual TIF files. Okay. Okay, it's pretty self-explanatory there. Load the 3D X-ray scan 1 slice at a time. Open the file name. What is this number here? This is, what the fuck is that? 65535? There's so much magic numbers here. Buffer, Z start, Z dim. Let's see. Okay, so these are different slices, right? Each scroll fragment has 65 slices. Mod 20, like that is no good. Then some rectangle with also kind of arbitrary ass numbers. A little bit of patch to show that. Then a sub-volume data set. You have your labels, you have your pixels, you have your image stack. Okay, this is actually going to train, so we should be able to see our computer should start doing things here. Yeah, it's using this first GPU. Name sub-volume dataset is not defined. Okay, sorry. Run that. Run that. You can hear the GPU working now. So uncomment that. Let's save. Let's actually interrupt, because we don't actually give a shit about training this right now. Let's do 100 training steps. Okay. And then let's come back down and rerun this. 100 training steps is fine. We're just basically debugging. Clear the memory before loading test fragments. Okay, so we have a little bogus training here. Let's put that there. Actually, we want this here. This is what we want. Put that in there. Run that. Already I can see we're gonna have to do something clever for this threshold. Okay, we have that. We'll run that afterwards. Here we can do from.utils import RLE encode. Let's go into our utils. All right, what we really want here where is he getting the ID here? Oh, he's not. He's just basically saying, he's just adding the same thing twice. Okay. This is really what we want here. So for each fragment in test fragments, and you're going to have a fragment ID and then the name of the fragment. You're going to need this predicted images, which is the output The problem is we're looking at two different things here. Yeah, he's saving all the images into this. Is this done? Okay, this is done. The threshold is done. And then what is the output variable here? Output. Torch zeros like label output. If you do the RLE of the output, what does that actually give you? Unable to import the required dependencies, no module named PyTZ. What the fuck is this? I've never heard of PyTZ. Apparently we need, is that just true in general? Like if we try to import pandas into like a generic terminal here, so we do Python import pandas as PD. Yeah, we don't have it. Okay, so pip install pytz. Okay. We run that. What is RLE output? It's just an empty string. Okay. Come here, predicted output. Let's just do this. See what we get there. Okay, basically empty strings, so kind of worthless. All right, clear all outputs. So let's go back to the Vesuvius challenge here and see if someone has a cleaner PyTorch data loader for this. Submissions. No submissions. Oh, those are my submissions. Leaderboard. Igor. Research engineer from Kiev. Okay, I don't think he submitted his code though. Let's go to code. PyTorch plus unet. Keras. Pixel coordinate generator. 100 times faster. What is this guy doing? TIF file names. The functions below produce all pixel coordinates for pixels within the rectangles and outside. So get the pixels. So everybody's like training on these little patches, basically. because these images are too big, so they basically feed them in patch by patch, is what I'm realizing. And that's what these buffers are, right? Is basically there's all this hard-coded crap about getting specific parts of the image. Okay. Let's see if someone's put that into a PyTorch. This guy has a UNet. See if he has a data loader. Oh, this guy has the summary writer for TensorBoard. That's good. We do need that. Random opt. Resize, load mask, load labels, load volume, sample random location, is in val zone, random patch lock dataset. I think this is actually what we want. Let's try this. Okay. So we have our nice little exploratory data notebook, but let's actually create separate files here. Let's make a new file. We'll call this dataset.py, and then we'll have a new file that we'll call model.py. So in dataset.py, we're going to, I guess, start from here. Let's format this just because it's like giving me a headache. Sort the imports. We don't need optim. Where does this get used? Oh my god, like some of the Python code that is in these Kaggle competitions is just out of control. Like, what the fuck? This guy's instantiating an object to set a like, I don't know if we should use this. I think we might be better off just making our own dataset object, just because this is, I can't trust these. All right, I'm gonna go to the bathroom. I'll think about whether we need to do that. And I will return. What's wrong, boo? Boo wanted to say hi. Say hi, Boo. What's up? You want to help us with the Vesuvius Papyrus Challenge? You're going to get a lot of internet points if you can solve it, Boo. She's a little Ashen Venus herself. Look at this. Look at you. Look at such a pretty little cat. Look at this beautiful little kitty. Say hi. Okay, that's enough. All right. So let's just create our own class here. Let's do class. We'll call this papyrus fragment dataset. Is that how you spell papyrus? Maybe I just don't use the word papyrus. class fragment dataset inheriting from the data.datasets object in PyTorch. Let's define our init class. There's going to be a variety of arguments here. We're going to have, of course, self, but we're also going to need height to resize all papyri. I don't think we quite want that. Let's also maximize this, get rid of that, open up a new side here. We'll put our exploratory data analysis there, and we can look at the actual data set, sub-volume data set that we were using before. So you have pixels, labels, and image stack. We're definitely going to need this buffer, whatever that is. So let's have a buffer here. This is going to be an int. We're going to set it to 64. Is that what the buffer is set to? Buffer size in X and Y direction. Half size of papyrus patches we'll use as model inputs. Okay, I kind of like this way of documenting arguments. I think it's better than doing it in the docstring. So you also need zdim, the number of slices in the z direction. Okay, let's do that. Number of slices in the z direction. Zdim will do 16. It seems like this guy has 10. First slice in the z direction. First slice in z direction, z start. You don't need the batch size quite yet. Anything else here? Prefix, buffer, zdim stack. I don't think we need anything else. Okay, what does this guy have here? He has shared height. I don't think you want to do this. I don't think you want to resize the image. That sounds like a terrible idea. So generating pixel lists. The pixels inside the rect are the val, the pixels outside are the train. Seems kind of complicated. What is image stack here? Image stack is torch.stack, torch from numpy image in images, image.open, this weird division here. And then he's slicing it. So you definitely need this. You definitely need the labels. And you definitely need the mask. Data-dir split index mask dot convert 1. Why is he resizing? And then torch from numpy. I think we can have functions for that. Let's do that. Let's have a load define load image mask. And there's a couple different masks here, right? We have the mask.png. Mask file name. This is a string, and this is going to be mask.png. Okay, we're also going to have ir.png, which is infrared. And then inklabels.png. Inklabels.png is the actual answer. Okay, that's what we want. So we have a load mask, load image mask, and then define load label, load image labels, image label, labels. Labels file name equals inklabels.png. That's correct. Let's have a data dir here. And let's also use a data dir here. Okay. So we're going to have functions for loading this, functions for loading this, and then do we need the IR? Does this guy use image open prefix.ir cmap gray? Are you even allowed to use the image.i or the IR? ir.png, I guess, maybe. Let's do here, define load image IR. ir.png. Okay. So the data dir, do we want to use pathlib or do we want to use strings? I think strings are probably fine. So let's do an assert. Make sure the data path or the data dir exists. I was like, can we write a decorator to put this assertion statement in there? Let's do mask file path. Is that similar thing here? File path and IR file path. Let's also assert okay. Let's assert here as well. Okay. So we have little helper functions for loading all three of those. I think these are going to be different types. What is the .gt.float.to device? What the fuck is this doing? Let's ask our good old friend ChatGPT. What is the .gt function call in this Python code doing? As a method greater than, it compares each element and returns the tensor with the same shape where the original tensor element is greater than the value and false other. GT0 is used to create a binary mask for a grayscale image. Okay, so another threshold. Okay. Returns a converted copy, translates pixels through the palette. What the fuck is this? L, RGB, or CMYK. When translating a color image to grayscale, mode L. Okay, so this is basically oh, wait, up here. Sorry, we were on that. Where is it? .convert here. The default method of converting grayscale or RGB into a bi-level mode 1 image uses Floyd-Steinberg dither to approximate the original image luminosity. I feel like maybe we don't actually want that. So let's come here, say image equals image.open. You're going to load the mask here of mask file path. Here, this is going to be the labels file path, and then here, this is going to be the IR file path. Let's also do a load image slice here. Load image slice. Data dir and then image slice. Or slice file name. So we're definitely going to have the data dir here. Directory containing the dataset, data dir, that's not going to be optional, that's going to be for sure required. We're going to have self.datadir, buffer zdim. Let's do a length function here. And let's also do a get item function here. Return subvolume ink label. Let's just say none for now. And for length, let's just return 1. Let's hard code it. Like, this seems very inefficient because you're taking the image, turning it into an NumPy array, then turning it into a torch array, then turning it into basically a tuple or a Boolean binary mask, and then turning it back into a float. So this doesn't make any fucking sense. All right. If we come here, we can say plt dot. Let's actually add a if viz equals, or if just viz, I guess, and then plt dot im show. From here, we're going to need import matplotlib.pyplot as plt, and then also import matplotlib. Maybe we don't need this. For all 3 of these, we're going to need a viz boolean. This is going to be false. All 3 of these, image, and I think for all 3 of these we can say return torch dot from numpy of np dot nd array of image. I think there might actually be a better way of doing that. Let's do a new chat. Is there a better way to, I don't want 3.5, I want GPT4. Is there a better way to put an image into a torch tensor than these lines of code? Let's get rid of this viz. I feel like there's something that's faster. There is a more efficient and recommended way to load an image into a PyTorch tensor using the Torch Vision package. Here's a better approach. Okay, we do have Torch Vision. Import Torch Vision. Load image to tensor. Image.open to tensor. Is this fucking real? Okay, maybe. Is this hallucinating? Convert a PIL image or ND array to scale the values accordingly. to tensor of image. Let's comment this one out for now. And let's actually delete this crap here. Load labels, load volume, sample random location, is in max zone, is in val zone, random patch dataset, get item. No. All right. I want to ensure that these image loading functions are correct right now. So we're going to do a if name. Come on, Copilot. You know what you need to do. There you go. I don't need this just yet. What I want to test is test the image loading functions. So I'm going to say data dir equals, this is going to be data, what was the path again? Data train 1. Data train 1. Mask equals load image mask, viz true. Labels equals load image labels, viz true. And IR equals load image IR, viz true. Okay. That is what I want right now. And let's actually run this. See what we get. Let's close out of that. Let's go back to our Ashen Venus. Let's run our Python dataset.py. No module named TensorBoard. Pip install TensorBoard. I think it's TensorBoard X. Sorry, you guys can't actually see this. Okay, so nothing actually happened here. Let's do PyTorch tensor, and then we'll print loaded image mask and return. Let's do something similar here. And loaded image IR. Okay, we're not going to need optimization. We're not going to need the neural net module. We're not going to need that. Probably don't need NumPy. Probably don't need summary writer either. And then sort imports. Let's run that again. Okay, plt.imshow, plt.show. plt.set title, I guess. mask file path. So let's copy that, put it in here as well. Except let's of course replace with that. And let's run it. Okay, so this is our mask.png. Cool. Close out of that. Next one is our inklabels.png. Cool, cool. Close out of that. And the last one here is the infrared. Cool, cool. Close out of that. So all of them are one channel, 8,181 pixels by 6,330 pixels. Perfect. Okay, so all three of these functions are pretty much the same. So I think we can basically make these into one function. Let's call it define load image. Copy paste all of this. Let's also import logging. Logger equals log, not logger, let's just call it log. And then log dot set level logging debug. We have our assertion. We have our file name. We have our image file path. Let's rename this. Let's call it image file path. Image open. PLT title image file path. PLT I am show image loaded. Here, let's change this into an F string, and then let's actually change this into the image file path here. And loaded image file path. Let's also change this to a log.info or a log.debug. Then let's do log.debug. Do the image shape. Let's also do like a little little tab, so it's nicely indented. And let's do the image type. Let's also do like min and max. Yeah, min, max, mean, std. So that means we can replace all these functions here now. And we can say load image, data dir, and let's say, what was the thing we needed? Image file name. Image file name equals, and we're going to do this with the multi-cursor. Let's do labels and then IR. And then we'll copy this, this, and this. Copy that, and then we're going to multi-cursor here. Put that in there. And then we can clean up this. We don't need these three functions anymore. So let's get rid of all of these functions. Load image mask, all this crap. So we have one load image function with asserts and debug. So it might be a little bit slow, but you know, we're kind of in the exploratory phase here. And let's go ahead and do that again. Let's rerun this and see what we get. Okay, got that first image, got that second image, got that third image, but we're not seeing any debug prints because I think here's where we need to log.set level, logging.debug. And then up here, we would actually log.setLevel logging.info. Come on. Why is this not showing? Why are we not getting debug logs on this? We do have the right. If we change these to infos. Ugh. What is going on? Why are we not seeing these? Log.debug. Loading. Let's change viz equals false for these here. Oh my god, come on. Let's copy paste this. Let's copy paste this into ChatGPT. ChatGPT will help us. It always knows the answer. Why am I not seeing debug logging prints when I run this Python script? Let's get rid of this dataset object though. You haven't configured the logging correctly? that's what it is. We need this one here. Copy, stop generating. What's the point of this fucking function if it doesn't do anything? Alright, there we go. Alright. So we have our mask. So 1 by 181 by 6330, float 32. 0, image max, image min, and image std. So these are all kind of close. Same thing with the labels. This is almost suspiciously similar to this. Are the labels floats or are they booleans? Let's see, let's make these true again. So this first one, I feel like it should just be booleans. The second one, I feel like it should also just be a boolean. This was the only one that shouldn't be a boolean. So, first let's do this second, just so we can visualize it nicer. Okay. If let's ask good old ChatGPT. Could you add some lines to this Python function such that it has a quarg that will load the image as a Boolean PyTorch tensor. Okay, well that's working. Let's go into our data set. So we're going to need a function that loads all the slices, right, which are TIF files. Those are different. We could probably actually ask ChatGPT for that as well. Can you modify the code inside the if viz conditional such that it plots the PyTorch tensor? Okay. Are we shooting ourselves in the foot by thresholding this? I feel like maybe we are. Let's see if we can actually load a TIF file. What's the name of this stuff again here? So we have a surface volume, and then inside there you have your TIF files. Okay. So data TIF equals load image, and this is going to be surface volume slash image.tif, or no, surface volume, and then we'll load whatever 00. Okay, let's see if that actually works. Before that, let's actually go and see what our we don't actually need this like weird stuff here, but now let's run this, see what we get. Let's import NumPy. Import NumPy as NP. And let's do these 3 lines here. Oh. All right, that's what we want. Cool, cool. It's also what we want. Cool, cool. It's also what we want. Cool, cool. Surface volume 0.tif. Looks like what we want. Perfect. Okay. I also think plt.imshow here, we can do cmap gray. Okay. So we have our image loading. We've tested it. It's correctly loading all the different types of images that we have for each scroll fragment. Now we need to start writing this data.datasets PyTorch class. So we're going to have our data dir. Let's move, actually, let's leave that there. Let's put this here. Actually, let's also assert as well. Let's add a couple more things here. So we want to add we want to basically take all these hard-coded paths here. So let's say self.tif or slices dir, and that's going to be that. And let's also assert that that exists. Okay. I feel like we want to load the image mask and the labels into memory. So let's do that as well. Let's do self.image mask file path. Or no, we can just do that. Yeah, that's fine. ink labels, and infrared. Let's do self.image mask file path, and then we'll have an assert there. Let's do the same with the labels and the assert that that exists, and then let's do the same with the image IRL file path and OS path exists. And let's load these into memory. So let's rename this, and let's call this load image tensor. Actually, wait up. Let's not do that. We're still going to call it load image, but we're actually going to output a data type here. This is going to be a torch.tensor. Import torch. Okay. So we're going to have to know the length. So I think in our init, yeah. First, let's actually see if we haven't broken anything. All right, so that's still looking good. That's still looking good. That's still looking good. And that is still looking good. Can we use the infrared as an additional learning target, or are they gonna... Are they not gonna allow that? Self.slices. Let's move this here. Let's actually take these and put them here. Let's go kill the Roomba real quick, though. Alright, we killed the Roomba. Okay. So, file names for the images. We have image mask. We have ink labels. We have ir.png, and then we have the slices dir file name. And we can actually go ahead and copy those 4 and replace with these. Okay. We'll add some comments. Load the auxiliary, or actually verify paths and directories for images and metadata. We'll have that be the comment for all of this. All right, so now that we have all the thing, we want to load the auxiliary, let's call it metadata. This is where we're going to have the, basically this here, IR, mask, and labels. The data dir. We don't actually need this. Yeah, okay, so we do kind of need it. We need it here. We need to do self dot and then delete all of this. And then here, comma. Come on, Copilot. Compute, compute, compute. There you go. Compute. Compute. Okay, so now you have the metadata, mask images. Load the slices, TIF files, into one tensor. This is where we could use the TQDM. For I slice path in enumerate TQDM glob os path dot join self slices dir with star dot tiff. Slice equals load image of the slice path. Yeah, let's actually change this here. Load image. Let's remove this here, and let's pass in the file path. We're going to have to change this code here as well. We're going to have to go like this. And do os.path.join data dir surface volume.tiff. Actually go backwards from the viz is easier. There we go. Okay. So now we no longer need this either. We can basically just delete the self.datadir part of this. All right, so now we have the mask, the labels, the infrared. We load the slices. If I equals 0, slice equals slice. Slices equals slice, else slices equals torch.cat. This isn't fast. Ideally, you want to pre-allocate. Say number of slices. This should be 64. Why is this like weird? And this should also return a dataset object here. Zmax 64. Here, assert that there are exactly Zmax slices. Expected slice count, call it that. Expected slices per fragment. That there are the correct amount of slices. Okay. So into one tensor, and then we want to pre-allocate. TF dot zeros. No, it's not TF. I'm in fucking PyTorch here. So the dimensions of the slices are going to be 8180 and 6330. Load a single slice to get the width and height. Load image, slices dir, self.width, self.height, slice width. Let's call this example slice. And then let's come here. Example slice shape 0, example slice shape 1. We'll do this and we'll say slice equals load image of slice path. We'll say, I don't think we need the actual enumerate, to be honest. Or yeah, we do, never mind, because we need to say slices of I equals slice. let's change this to slice. Print some information about our slices. Slices shape, slices type, slices min, slices max, slices mean. All right. So let's go ahead and try to instantiate, test the dataset class. Dataset equals fragment dataset, datadir equals datadir. It should just be datadir. Datadir is a argument and not a keyword argument. So let's go ahead, let's comment out these. Let's copy that, put it here, and let's run this, see what we get. Image file mass.png does not exist. What line is this? Line 19 in load image, but before that it's line 83, which is this one here. So this should be file path, not file name. So all three of these, file path. Expected 64 slices, but found 65. Huh. Is it going to be 0 indexed? Yeah, there is 65 total slices. Okay. 65. Let's add a log.info here. Initializing fragment dataset. Log.info. Loaded slices into tensor. And we'll do slices.shape. Okay. Okay, so this is erroring out because the target size of 1818081 tensor size 81816330. Expanded size of the tensor. Okay. So the problem here is that when we load this slice and then we create a zeros that has this many slices in the channels, then 0, then 1. Then slices of I like this, I think is what we want. I think these are backwards. I think it's like this. All right, we're putting a breakpoint in here. Import PDB, pdb.set trace, and we're also going to put a breakpoint in here. Let's rerun this. All right, so our slices is a 65 by 8181 by 1. Okay, I see what the issue is. So this is slice.shape 2. All right, slices is 65 by 8181 by 6330, which is correct. And then if we continue, slice.shape is 1 by 8181 by 6330. All right, it's working. Let's get rid of our traces. And we pretty much have a working data loader here, right? So the thing now is that basically we're going to want an infinite data set, right? Because we have our papyrus fragment, and then we're going to basically want to cut it or take little patches of it, right? Then these patches are going to be of this right here. Start and dim and buffer. So this is basically the size of our 3D kernel. So I have a Python code for a PyTorch data set class. The data set is 3D patches of a 3D tensor. I want you to create the tensor. The patches will have some length or some height, width, and depth, which should be quargs to the dataset class. Can you create a PyTorch dataset class that generates random slices or random patches of random patches? Let's see if that's enough. Okay, so I like how the length here is correct. You're going to be able to get the length from the dimensions of this slices tensor here. So let's go ahead and we're going to call this scroll, or actually fragment. We're going to put that there. Let's rename this so it's self.fragment.shape. So let's not call this buffer zdim and start. Let's size of patches dataset. Fragment patches dataset. Size of an individual patch. So let's say patch size X, Y, and Z. Let's actually put this here. I don't like how this is like very weirdly formatted. Okay. So we want to make some assertions on the patch size. Right? Make sure the patch sizes are valid assert the patch size is less than the fragment shape. Yep, that's what we want. That should be less than that, and then that should be less than that. That is correct. Now we need to know maximum number of patches from one. No, I think this is where we need to pad. Pad the fragment to make sure we can get patches from the edges. Okay. What is f.pad here? This is a functional. Okay, so we're going to pad the fragment. We're going to pad the x by self.patch size over 2. Self.patch size, put this up here. X over 2, self.patch size y over 2, y over 2, z over 2, and z over 2. Okay, that seems correct. Okay. Let's store here. So let's actually say self.fragment size x, size y, and then size z. And then here, yeah, we can just use those. And the length of this is going to be, no, not the actual shape tensors here, but because once we pad it, size x, okay. Get an item. There's going to be an index. Okay, and then why don't we also add a viz equals here so we can actually visualize that. And we're going to get the x, y, and z indices. Yes. 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 Okay, get the patch. That also seems correct. Get the mask and labels for this patch. Okay, we're going to import the matplotlib patches here. So that we can visualize here. If viz that's not what we want. We want the patches here. Like this. PLT show ax.add patch. So we're going to have 3 plots. The 3 plots okay. The first of our plots is going to be the patch itself. The second one is going to be the mask and then the labels. And actually, why don't we do 4 and then the first one here, and then the last one is going to be the actual visualize the bounding box. And then we'll say axes 3, add patch, and then plt.show. So we're going to return the patch, the mask, and then I guess the label. Labels should be a single number though, so I think this might be wrong here. Okay, let's see if this even runs anymore. This is going to be a pain to debug because we're going to have to do this every time. Okay, it does run. Let's import PDB here. And let's run this. While that's running, let's close out of this. Let's save. Let's go into our model.py and let's go ahead and make a model. We can just copy the one from the example for now. Import torch. Import torch NN. That's the model. If name equals main, test the model. See if let's make a little function here. Define import torch. Import logging. Log. Let's copy paste our dataset logging here in our utils. Get device. Yeah, that's exactly what we want. Let's go back to our terminal. Dataset dot get item. Is that what it's called? Get item. Of 0 and we'll say viz equals true. Fragment patches dataset has no attribute image mask. Yeah, right here. We need to self.image, or it's not going to be image actually, it's just going to be mask labels and IR. So here we can get rid of this. Okay, exit out of that, run that again, let that go while we continue to mess with this. Let's say from utils import get device. Say device equals get device, and model to device y dot shape. Actually, we don't want any of that. So we're back here. Dataset.getItem 0 viz equals true. Invalid shape for image data. I think that's the problem here. So we need to do this shit again. Dot transpose 120. So let's actually put the breakpoint here. And exit out of that, rerun that. While that's going, let's ask GPT to write us this model in the torch model class. Can you write this model as a class? All right, we're back here. We're in the trace. Let's say dataset.getItem 0 viz equals true. Fuck. Okay, we need to go back here. Get rid of this. Just put that there. For I range length dataset, dataset I. It's not how you want to use that. Okay, we have this one again. Here, dataset dot get item of I viz true if I is greater than 3 break. Random randint from 0 to length data set. Let's actually import random here. Okay. We can run this. Let's also do a new file. We'll call this train.py. Here's where we're actually going to have our train loop. So we're going to have a train eval loop. And we're going to the reason we're going to have that inside a function is because later we're going to use a hyperparameter optimizer as well. So we're going to have to import model, or from model import from utils import get device and make submission. Now let's just get device for now. And then from data set import, specifically we want fragment patches dataset. Okay. So we're going to have a train data directory. Let's see if our code is here. Int object is not iterable. Well, it's because we did it wrong. It should be for I in for blank in range 3. I equals random int. So this will just pick 3 random indices. Okay, so our train eval loop is going to be get the device. Okay. Load the model, load the data set. This is going to be the train data set. Or actually load the data set, yeah, train. Split data set into train and test. Length dataset minus train size. Data.random.split dataset train dataset size. It looks like this is using the torch.data util here. need the actual data dir. This is going to be a string, and this is going to be, no, this is going to be data train 1. All right, one thing we can actually do here is do this. Star quargs, and then we actually pass the quargs there as well, and then the quargs here. This is sometimes dangerous, because basically what's going to happen is that if you have any quargs that are the same here and in the model function, then you can get kind of very terrible errors. But this is also a very easy way to basically future-proof your code, because now you don't have to be messing around with quargs. You just pass them in like that. Okay. Then there's going to be the actual create the data loaders. Creating a data loader. We're going to need a batch size here. Oh shit, what the fuck happened there? Batch size. We're going to need a learning rate. Let's just call it LR. Everybody calls it LR anyways. Create the data loaders. The train is going to have batch size. The test is going to have batch size. The test is going to have shuffle equals false. Create optimizers. Okay, we're going to need import torch here. And I'm going to actually do the loop. We're going to need epoch. Epochs. Initially, just 2 epochs is fine. For epoch in range epochs. Come on, Copilot. Oh, Copilot pooped out. Didn't want to give us the answer. Okay. Let's go here. All right, so we're in our function here. What is the shape of this patch? It's 1 by 256, 256. What is the shape of the mask? That is not correct. What is the shape of the label? That is also not correct. Okay. So let's go into our data set here. Let's make these a little bit smaller too. The size of the patches X should be something more like a 8 by 8 by 4. How about something like that? So it's 4 deep and then 8 by 8. And let's add some debugs here. Log.debug. Z index is Z out of that X and Y. And let's also do dataset index. Dataset index is index out of length. Okay. This should be here. Let's put some little tabs here so it's a little bit easier to see. Okay. This is not correct. Because we actually want z plus patch size over 2 minus z plus patch size over 2 we should actually store these values. Store the half sizes of the patches. All right, and then here we can actually get rid of that and regenerate it. And this should be fine. This here, we can now regenerate this. No, that is not correct. We need z minus self dot patch size x to z plus x to x plus, and then y to y plus. That is correct. Get the mask and the labels. This is also going to be the same. And labels equals self dot labels x y. Nope, this is not right. This is x minus self dot patch half size and y minus self dot patch half size. And we're actually going to need to we're going to need to pad these as well. We're going to need to pad the masks and the labels as well. Yeah, that's unfortunate. Okay. Okay. So we need to create padded versions of our mask and our labels. Actually, we don't need that. The label is just going to be the center. Yeah, I'm pretty sure this might just be this. And then we don't actually need get the patch and label. We'll call this label. And labels is so this is going to be the 0xy like that. Labels what you return here. Here we still have our set trace. We no longer need these. we should have a to-do here. 3D visualization. And then visualize the bounding box. Let's run this. All right. So going back to our model, let's do 3D CNN, so 3D ConvNet. We can't start with that. CNN 3D, how about that? We can actually make this even smaller. So let's go to our matplotlib here, and we'll say, or not our matplotlib, our ChatGPT, and we'll say, can you modify, or can you create a PyTorch model similar to the one below, except it is smaller and simpler? The input for the model will be a tensor of shape B CH B, and then we'll have like, I don't know, like 488. All right, we're back here. So what is our patch? Patch.shape. It's an 8x8x4. Right, what is our label? Our label is 0. Visualize the bounding box. Let's do patch 0 numpy. Okay. If we hit continue here, what happens? Okay, so that's our patch. So this is actually the wrong dimension here. This needs to be all blank blank 0. Here, the 3D visualization, why don't we actually do a subplot? So figure axis subplots, there's going to be fragment size z, which is the depth. There's going to be exactly that amount. Sorry, fragment size z. and then +1, because we're going to need to have the so this goes here. So first plot, visualize the bounding or the patch in the grayscale, or in the infrared image. Okay, so first thing you do is ax0.im show of ir0 all numpy gray. So I think you can just do this. Then add the patch. And then visualize each depth of the patch. For that, IM patch, and this is going to be yeah, that was actually right. All right, let's get rid of this trace. And let's run this. What's going on here? Oh, we need to close out of that. Okay. Let's run that. There should be something better here. We should to do should label be average of patch, center of patch? Not entirely certain, right? We need to do this crap. Right here. Move this here. Delete that. Let's make it a little thicker on the line here. Line width 10. Okay. Let's try that. So clear the outputs here. Here's a problem. We're calling this patch. Let's call this bbox. Let's rerun that. All right, we're like over 3 hours now. I think we might have to take a break, maybe do some eating, and then come back to this. What is out of bounds here? I think that is fine. It's just this one here, this patch. Let's try that. All right, we're going back here. Log.info. We need the log here, so let's import logging. Let's copy paste our logging boilerplate from here. There's our logging boilerplate. Let's POC 1 of 1. Let's return here best eval loss. This is going to return a single number, which is going to be our best, maybe not best score. So we're going to have to keep track of that. Best score is 0. Train with torch no grad. This is going to be the test. We're going to need TQDM. Here we got image label. Do we need the no-grad? Can we just do model.eval? Ooh. Then the image. Or it's not an image, it's a patch. There's a patch and then there's a label. The model predicts a pred. And then our loss is just a binary classification loss. There's our BCE loss. Get that. Loss equals loss function, predicted labels. No, this is we're doing wrong shit here. Let's go back to the data set. Index 4 is out of bounds for dimension 2 with size 4. Should be I minus 1. Because it's not fragment, it's patch size. This is wrong. This is patch size Z. Here, this should be patch size Z. Yeah, I think that's what it's supposed to be. Let's run that. So let's make submission. I'm gonna have to figure out how to do that. That just seems so gross. Okay, this did something. What did it do? It did this. I do not see the rectangle. Oh, okay, you see it's very, very faint, but it is right there. Is the anchor point the bottom corner? Yeah. Okay, that's why. The anchor point is the bottom left corner. So we got to actually calculate that. B box anchor is equal to that, and then here got to rewrite it. Let's also make this a lot thicker. All right. So, I mean, there is a red there. It's just like very bad. Can't see anything. God, I think this is still wrong here. Rectangle. X, Y, tuple, rectangle width, rectangle height, rotation point. Let's put a breakpoint here. It might also just be that the patch is just too small to even see anything here. Let's do something a little bit bigger. Let's do 64 by 64. But let's still put a debug here to make sure. No, let's just run it. Let's just send it, as the Zoomers say. Okay. We're getting the patch. Let's run it again. Oh yeah, we were asking ChatGPT for an easier one. All right, look at that. So this is this tiny little patch, right, of this particular thing. This is just showing you how crazy the resolution of an X-ray is, right? Where like this right here is what the data looks like, and then that is the zoomed in. So this tiny piece of scroll, which must be like this big, right? Like we're talking like something like this, right? And then within that, we're looking at an even tinier little section of it. And then inside that super tiny little section, we even have slices vertically. So these are the vertical slices. So it's cool. So, I mean, this data is so dense that basically what our data loader is doing is it's going to create kind of infinite data from that. So I don't like this. I don't know why this is being compressed. I guess we should probably have some kind of check where if the patch is not within the mask, then it shouldn't count. Yeah, okay, so let's add that. Let's add a little to-do. So here we should have a to-do. Make sure only indices that are within the mask are valid. All right, so then we're going to basically have some like indices kind of thing going on here. Okay, we're at 3.5 hours. This is getting a little bit ridiculous. I need to go eat. So I'm going to push all this. We have our EDA, our train, our model, and our utils. Let's add all of these. Semi-working data loader. And we'll commit all of this. All right, so we have our semi-working data loader. We are on our way. Doesn't look like very many people stayed, but I mean, I guess it makes sense. It's kind of intense. Looking forward to this. You know, this has got me excited. I'm into this challenge. We'll see what we can do. Thanks for listening, and see you guys potentially in an hour.